Hello, this is Rahul and welcome to the third experiment of Digital Signal Processing Lab. Today we are going to discuss the period of a signal using Discrete Fourier Transform. First of all, let's look at Discrete Fourier Transform. Discrete Fourier Transform is a finite sequence of equally spaced samples of a function into a same length sequence of equally spaced samples of discrete time Fourier transform, which is a complex valued function of frequency. The formula for the discrete Fourier transform is as follows: f of n equal to sigma k equal to 0 to n minus 1 f of k into e power minus j 2 pi by n into nk. This exponential part is also known as the basis function. Now let's look at the matrix form representation of discrete Fourier transform. Here f of 0, f of 1, f of 2 and f of n minus 1 are the Fourier transform coefficients, and this matrix is the orthogonal matrix which is formed by the basis function, and these f of 0, f of 1 and f of 2 are the original input signal values. Here w equal to exponential of minus j into 2 pi by n, and this orthogonal matrix follows the symmetric property, periodicity property and also the orthogonality property. Now let's look at some applications of discrete Fourier transform. Discrete Fourier transform helps in the analysis of spectral components of the signal and also in determining the frequency response of a system. It is also used in filtering of a signal and also helps in an efficient way of implementation of autocorrelation and convolution. Now let's look at the calculation of BPM for a PPG signal using discrete Fourier transform method. Here we compute the dominant frequency Fk as Kmax into Fs by n, and the beats per minute is given as 60 into Fk. The formula is 60 into Kmax into Fs by n. Here the main idea regarding the beats per minute or the dominant frequency calculation is that we find out the Kmax value in the discrete Fourier domain. Now let's look at the code for finding the period and beats per minute of a PPG signal using discrete Fourier transform. The code is as follows. Initially, we filter the original signal using the moving average filter of length 10 here mentioned, and then the filtered signal is then converted into the Fourier domain, discrete Fourier domain, using this part of the code. And here in the Arduino software we need to install a library for complex variables, for determining complex variables or calculations, or else we need to follow the original cosine and sine procedure for computing the magnitude spectrum of the original signal. Here, after getting the discrete Fourier transform, we then compute the magnitude spectrum by squaring the real part and imaginary part, and then taking that whole value under root. Then we can also plot the discrete Fourier transform graph, and then after that we need to find the first peak value in the discrete Fourier transformed function. So we initialize two variables, max value of 1, max value of 0, and the total length of the signal is 75, and so between 0 to half of the length, that is 0 to 38, we get one max value, and from 38 to 75 we get another max value. But here the first maximum value is of our interest, so we store the index of the peak value in index 2 variable, and then the beats per minute for using DFT can be calculated as the index 2 into 25 into 60 by 75. Here index 2 is the Kmax value of the original PPG signal in discrete Fourier domain. Now we can also verify the code using the autocorrelation function as depicted in the previous lab experiment, and the period can also be calculated. For further information, please go to the previous video in this series, and the beats per minute using autocorrelation method is also found. The results are as follows. Here we can observe that the beats per minute using discrete Fourier transform method is 80 beats per minute, and beats per minute for using autocorrelation is 71.43, and the error is not that much. And the magnitude response plot of a PPG signal in Arduino is as follows. Here we can observe the two peaks in one time instant, and we calculate the peak index of this peak position only here. And we can also verify the same magnitude response and beats per minute in the using MATLAB software, and the code is as follows. Similarly, this is the moving average filter part of the signal. This part is used for computing the DFT of the signal, and this one for plotting the waveforms, and then finding the maximum value up to half length of the signal, that is from 1 to 38, and then printing the beats per minute value by using the formula, and then cross-checking with the autocorrelation function. Similarly, in MATLAB also we can verify our results. Now the results are as follows. Here we obtain the same results as obtained using the Arduino software. BPM using DFT is 80 beats per minute, and BPM using autocorrelation is 71.4281. That is not that much. And similarly, the magnitude response of the PPG signal in MATLAB is as follows. Similar plots are observed, and autocorrelation plot of the PPG signal in MATLAB. The results are as follows in both Arduino and MATLAB software. Beats per minute is the same, and BPM using ACF is slightly different due to the float type variable. And the conclusion, the beats per minute of PPG signal is calculated using both autocorrelation and DFT procedures in Arduino as well as MATLAB softwares, and the results appear to be the same. Thank you for watching my video. I hope you like it.